Today, my topic is going to talk about the competitive and the cooperative heterogeneous deep reinforcement learning. This content will have I'll have 4 parts. First of all, I will introduce the motivation, and then I will simply introduce our method C2HRL, and then I will introduce the experiments. And the last part is the conclusion. First of all, the motivation is first, there's no clear DRI agent that can consistently outperforms the others in every task, and no one method can adapt to all tasks. Secondly, there's diverse agents can contribute the exploration process by generating diverse experience, which can be employed by the off-policy agent. These pictures show the overall structures of our method. Our method have two parts. The left part is the competitive exploitation part. The right part is the cooperative exploration. For this competitive exploitation part, we have heterogeneous agent pools, which have diverse agents, probably have different learning algorithms or structures, and we search the best agent for this agent pool during each iteration, and then we employ this agent to the environment to do our exploitation, and then store experience to a global shared memories, which is a two level memories. The shared memories is just store every experience, and the high value memories is store the experience which have a higher return. This is a circle for 1 iterations, and during the whole learning process, this process will keep learning for many iteration. Okay, now I introduce the details of the competitive exploitation part. So, how to choose the right agent during each iterations? We use the upper confidence bound technique, but the general USB technique cannot apply directly in our settings, because in our frameworks there are multiple diverse agents which have a very different performance. For example, the gradient-free agent, such as the evolutionary algorithms. These agents can grow, and performance can grow up very fast in the beginnings, but will probably stop grow the performance during the later learning process. So for such agent, the normal USB technique is not is infeasible for applying this agent. To solve these issues, we introduce a technique called growth abilities. We use the agents returns during each iterations to determine whether this agent have a good performance during such a iteration. For this equation, which is showing this equation, the Rj and Rj plus 1 means two iterations, the current iteration and the lost iterations. We use this to show the agent's growth abilities. Secondly, we also try to keep improved exploration diverse and maintain the stabilities. because in the beginnings of the exploration process, we encourage the different agents to explore the different solution space. They we encourage this exploration process, but during the later process, we try to keep the learning process as more stable as much as possible to keep this whole learning process stable. So we also introduce another to introduce this equation to try to keep the whole process more stable. We use the agent's current time steps divided this whole time steps across from all agents. We use this thing to normalize these growth abilities. So combine these two parts, we have the new USB score just for this equation. Okay. There's, secondly, we use this part is about the cooperative exploration part. We use a two-level shell memory buffers to try to make the learning more effective. For this feature, these different agents, every agent search the different part of the space, and then they store all this experience into a two-level memories. We use the episodes returns. If this episode returns just bigger than threshold, and then we decided to store this episode experience into a high value memories. But yes, there are some other works just similar to this concept, but this difference is our method this difference in our method is that our methods just collect the experience for diverse agents. So we didn't use the maximum returns. Didn't use the history maximum return to decide to whether store or not. But instead we use the minimum returns because we try to keep the experience diverse in our memories. And secondly, our different agent sample for these high value memories, they can employ different possibilities, not the same, not just one possibilities. For example, the agent zeros can sample this for these high value memories use higher possibilities, but agent one can sample for this high value memories use a relative lower possibility. Through this way, we try to make these different agents explorations can work in a cooperative way to improve the agent's performance. This now I can introduce the experiments. We evaluate the R method on 6 magical tasks to show its sample efficiency and stabilities. And all these scores come from the average final scores across 5 Cs. We compare with our method to the other state-of-art method. For example, the C2HRL is also a hybrid method. The SACs and the TD3 are the state-of-art of policy RL agent. We also employ the SAC and the TD3 in our framework to they also work as the agent. For this table, we can see our method achieved the best performance average return and the stability, so which is the variance. The variance also is smaller than other method. We also make our experiments to investigate the competitive resources redistributions. This experiments is try to show how C2HRs distributed resources across different valencies. For this table, we can see the task humanoid and swimmers. These two tasks, they our framework almost distribute all the resources to SAC agent and the EA agent, but the other 4 tasks, the resources distributions is not the same. They have different based agent across different valencies. So which means there are this USB score is works in such cases. These ablation studies, we try to figure out whether this key component whether works in our framework or not. So to investigate this two-part, we propose C2HR-HM, which is without the shared high-value memories, and the C2HRL plus GC, which is the version without our gross capacity metric. Okay, for this, the left part is the C2HR plus HM. The right is the C2HR plus GC. For this experiments, we can also see that these two key components really works in our framework, especially the growth abilities. Which have a very crucial impact on the final performance. Okay, conclusion. In this work, we present C2HRs or scalable framework that allows gradient-based R learners and gradient-free EA agent to jointly explore and exploit solutions for the deep reinforcement learning problems. And we conduct experiments in a range of continuous control tasks, which demonstrate that C2HRs can outperform the other baselines in both sample efficiencies and stabilities. And but the shortcomings of our method is that as our method is trained based on multiple selected agents, so its final performance depends on this construction of the agent pools. Moreover, our method also introduced some new hyperparameters, such as the sample possibilities for the high-value memories. Okay, finish. Thank you.
Any question from the audience?
Hi, thanks for your presentation. I have some questions. The first is, can your method also scale to some image-based control task like the DeepMind control suite, and also other high-dimensional space like video games?
Yeah. Our method is I think our method can apply to such a method, because our frameworks we test our frameworks also on high dimensional tasks. Is the emoji call, which is also high dimensional tasks, but it's not based on image. It's based on a continuous control tasks.
Yeah, I see. In the Mujoco, the state is vector-based. So in the image-based control, in the demand control field, it seems much difficult than vector-based task. In image-based control, which is previously dominated by some model-based RL. So I'm curious if your method can generalize to this task.
Yes, of course, because our method don't kill the agents, how these agents applied. Our method is built on the top of these diverse agents. We don't kill how these agents is implemented.
Okay, thank you. My second question is, I see that you train a pool of agents. So how about your training cost compared to other methods?
Our training method is because that depends on this the agent you choose. In our experiments, our computation task is mainly come from the SAC agent or TDC agent, which is a gradient-based method, which is very slow. But if this task, for some other tasks, for some example, the swimmer tasks, this task will be much faster than the SAC or TDC because our framework will choose this gradient-free agent more often than the gradient-based. So basically, our computation task is just, I think it's just slightly higher than the based agent.
Okay, thank you.
Any other questions from other audience? Okay, maybe.